Hello everyone, this is Roman Mars, and today we are continuing with chapter 2, and now we're looking at subtopic 2, forces. In this video we're going to look at free body diagrams and forces, net force, friction, first, second, and third laws. So what's a force? Force is simply put a push or a pull, which implies direction, meaning forces are vectors. We'll talk about force and what it actually is in a little bit. Weight is a force of gravity that creates acceleration due to gravity that we discussed in the previous video. The direction of weight is always downwards towards the center of Earth, just like gravitational acceleration. The formula for weight equals to mass times gravity, or mg, where g is usually 10 meters per second squared, or 9.8, and m stands for mass of an object in kilograms. The normal force is what is called a counterforce to weight and is perpendicular to the surface where a certain object is positioned. So there are a few types of forces that we'll need to know. There's tension, which is denoted by T. It can only be a pull and never a push. Friction, which was denoted by F with a small little f next to it, tries to oppose the motion. So if you try to move an object to the right, friction force will be to the left. The friction is always parallel to the contact surface, meaning if you're moving that object horizontally to the right, friction will be horizontally to the left. The normal force, which is denoted by R or sometimes N, is perpendicular to contact surface, which we discussed in the previous slide. Friction and normal forces are mutually perpendicular, meaning they are always perpendicular to each other. And friction and normal are also what's called surface contact forces. Those are forces that are created because there's a surface with which the object has a contact with. And weight is what is called an action at a distance force, meaning the source of weight does not actually have to touch the object, meaning it's not a surface contact force. In free body diagrams and just any diagrams in general, weight is sketched from the center of an object and always towards the center of gravity. Usually it's down. Normal is always perpendicular to the contact surface. Friction is parallel to contact surface, and tension is sketched at whatever angle it is given. At the bottom we have two diagrams, a normal diagram which shows forces, and on the right we have what's called a free body diagram. So let's look at the left one first. Here we can see there's a certain block that is resting on some surface. The forces that are acting on it are weight, which is going from the center downwards, normal, which is denoted by R. It's perpendicular to the contact surface, and as we can see here, that is exactly upwards, as our contact surface is parallel to the ground or the bottom of your screen. Tension, which is the force that we pull with on this object. If you try to pull an object to the right, there will be friction that will be on the opposite direction, to the left, and it's also perpendicular to the normal force, and it's parallel to the contact surface. On the right we can see the same setup, however it's more generic. The block is represented by a single point, which could in reality be denoting any object. It doesn't have to be exactly a block. So this is why it's called a free body diagram. It could be used for any object, and all of the forces are drawn from that point. So we have surface 1 and 2, and when they come together the peaks of those surfaces will each surface at atomic level has small peaks because no real material is 100% smooth. So at first, when you apply sideways force to it, which is the green arrow, which represents the green arrow, these cold wells, they do not let the surface 1 to actually move because they create friction force, static friction force. If you apply enough force to surface 1, the static friction force will reach its maximum. And after exceeding that maximum value of static friction, if your tension is above that value, surface 1 will move and there will be less peaks that cold well. Now let's look at the graph to understand this a little better. On this graph, green circles represent the tension at a given point of time, while the red circles show friction at that same time. So at first, as we increase tension linearly, our friction at that point, still static, increases at the same rate. You can see when the static friction force reaches its maximum, applying any further tension will decrease the friction, and it will be dynamic friction. And it doesn't matter how strong the tension is, as long as it's not below that maximum friction force, dynamic friction will be constant, and at that time the object will be moving just like surface 1 did. Let's look at the two formulas on the bottom for friction. The force of friction, if it's static, will be less than or equal to the coefficient of static friction, which is denoted by mu s, and which is multiplied by normal force. It will be less than or equal to, because coefficient of static friction and multiplied by the normal force define the maximum value of static friction. Static friction can be less than that value, or it can be that value itself. While dynamic friction is defined as force of friction equals to the coefficient of dynamic friction times normal force. As we have already discussed, dynamic friction is smaller than than the maximum value of a static friction, which means that the coefficient of dynamic friction will also be smaller than coefficient of static friction. Both of those formulas can be found in physics data booklet. Now let's talk about Newton's first law. Newton's first law is drawn from the concept that he himself created of the net force and Galileo's concept of inertia. This law says that the velocity of the object will not change if there is no net force acting on it. When the net force equals 0, it is sometimes called the condition of translational equilibrium. So now let's look at this example. A 1,000-kilogram plane is flying at a constant velocity of 125 meters per second. Label and determine the values of the weight, the lift, the drag, and thrust if the drag is known to be at 25,000 newtons. So first of all, we draw a free body diagram. We know the weight is downwards, lift is upwards, drag would be in the opposite direction of thrust, both of them being in horizontal direction. Since we know that the velocity is constant as given in the question, we can apply our knowledge of first Newton's law. Thus, the sum of forces in the x and the sum of forces in the y directions will equal to 0. We know that the weight equals to mg, which would give, and plugging in mass and gravity, gravity being 10 meters per second, we can find that the weight of the airplane is 10,000 newtons, and it's downwards. Since we know that the vector sum of all forces in vertical direction is 0, lift minus weight has to equal to 0. So the magnitude of lift equals to the magnitude of weight, which would make lift equal to 1,000 newtons upward direction. We know that drag is 25,000 newtons, and we know that it tries to impede the aircraft, as it's similar to the friction force. So we can say that D equals to 25,000 newtons to the left. Since, due to Newton's first law, the sum of all forces in direction x has to equal to 0, thrust minus drag would have to equal to 0. So the magnitude of both of those equal to 25,000 newtons, where thrust would equal to 25,000 newtons to the right. Now let's talk about Newton's second law. The acceleration of an object is proportional to the net force acting on it, and inversely proportional to its mass. So in the formula, that would mean that A acceleration equals to F net divided by m. Or we can rearrange for net force, which will give us the following formula. Net force equals mass times acceleration. Here we can see that Newton's first law is a special case of the second Newton's law, specifically when acceleration is 0, meaning there's a constant velocity. So here we can see a more clear definition of a force, because there's a formulaic way to express any sort of force. Now let's look at another example to understand the second law better. The same 1,000 kilogram plane is flying perfectly level flight. The drag is 25,000 newtons and the thrust is 40,000 newtons. Find acceleration of the plane. Since the flight is leveled, we know that the sum of all vertical forces has to equal to 0. Now that we dealt with vertical component, we need to deal with horizontal. The sum of horizontal forces equals to thrust minus drag, because they are in the opposite direction. So by plugging in for 40,000 for thrust and 25,000 for drag, we get the net force of 15,000. From Newton's second law, we know that F equals ma. From that, we get 15,000 equals 1,000 times acceleration, or acceleration equals 15 meters per second squared. Now let's go to Newton's third law. Simply put, for every action force, there's an equal and opposite reaction force. So every time you push on an object, that object pushes on you in the opposite direction of how you pushed it, but with the same magnitude. If we put it in the formula, force AB equals to negative force BA, where force AB is the force on body A applied by body B, and similarly force BA is the force on body B created by body A. Each force of the action-reaction pair acts on a different mass. In a system, internal forces are forces that occur during interactions between objects in the system. Example would be collision between objects. While external forces have external origins. For example, weight, friction, and normal force. If the system contains of two balls hitting on each other, the internal forces would be a collision forces between those two objects, while external forces would be the weight of each ball, the normal force of each ball, the friction created between ball and the surface. So there you go. That was chapter 2, subtopic 2 for you. Tune in for chapter 2.3.